Good morning, my dear students. Welcome to today's lecture of computer organization and architecture. Today I will be taking the topic instruction formats. Myself, Dr. Akhilesh Verma from Department of Computer Science and Engineering. So let's proceed for the today's topic, instruction format. Computer may have several instructions and they have various lengths, and they have several varying number of addresses for the operands. So, number of address fields in this instruction format of a computer determines how you refer the various registers. So, most of the computers are classified based on these ways into three organizations. That first one is single accumulator, second one is general register organization, and the last one is the stack organization. So, based on the format, and the format includes the length and the way it is addressing the data that is being used by the instruction, we classify the organization of a computer or CPU into three different organizations: single accumulator, general organization, and stack organization. Now, there is a very important term that is called as ISA, instruction set architecture. Now, this is an important terminology to be understood by students, because it totally depends upon the how the internal processor or storage and the naming convention is followed. Okay, so consider if we have a instruction set, okay, 1, okay, so it will have different ways to store or refer the data, and they have different naming conventions. Okay, likewise, if there is another instruction set computer 2, so for that case the storage reference and the naming convention will vary. Okay, so ISA means the set of instructions that a organization supports for storage, or like it is the language basic instructions that is available by a organization that can be executed. So, ISAs are categorized now again in the same manner as we have talked about in the previous slide, how the formats are understood, and formats are varied with respect to the organization. Similarly, with the instruction set architecture, we can also think in the same manner that the ISAs are categorized based on where the operands are, that is stored, and how explicitly or implicitly we access their data. Okay, so based on the addressing scheme and what are the length and what are the operations that are performed, we can classify the computer in terms of different organization and instruction set architectures. So, now we understand and know previously that there is a term translation and high level program like C code. Okay, it is being translated into assembly code like MIPS. Okay, so ultimately this translation to machine language, that is called as representation of instructions in zeros and one, is done by a software that is called as compiler and assembler, and this is the translation process that happens when a computer hardware executes any higher level code. Now, if you see ultimately the computer executes a machine code on the processor. So, this machine code is to be understood by the computer programmer to understand the clarity how efficiently that processor will work. So, if we see, we write a high level code, that is C program. In the step 2, the compiler comes and it generates assembly code. Okay, and in the step 3, this assembly code is used by assembler to generate the binary code. Now, this binary code, or you can say binary machine code, is used at the processor level. So, processor level use this machine code to refer a particular storage, okay, or it can refer to what a particular operation or the address fields that is needed to execute a particular instruction. Okay, so ultimately the instruction format totally depends upon the final machine code, which is output of the translator and assembler for a particular processor. For particular processor, it will be different. Now, the first classification that is classified for the processor is the single accumulator organization. In this, only one general purpose register is designated, and that is called as accumulator. Okay, so you can see I have marked here, this is the accumulator, and the accumulator necessarily stores one of the operands. Okay, out of two, one operand will be present in the accumulator. The other operands is specified along with the instruction. Fine. So, when a CPU organization have a data access from data access from the accumulator, that particular organization is called a general register organization. So, first data is taken from this accumulator and the second data is taken from the another memory location. Okay. So, this is called a one general purpose register. On other hand, we can generalize this general purpose single accumulator to many registers. So, that is called a general register organization. All the operands are explicitly specified. Okay. Now, you have choice to exercise explicit data. Earlier, there was one explicit choice is there, other was fixed, that is accumulator. The further classified based on they are further classified how you are taking, both are from the register to register or register to memory or memory to memory. Okay. So, when the operands are stored in the register, when operands are in register and other in the memory, and another operand that both are in memory. Okay. So, you can see here we use mux. We have already discussed that mux is the selection unit that selects the data. Either we have to select from the register or either we have to select from the outside world. Usually outside world is the memory. Fine. Or we can have all these three combination, means first one both the data is from the register itself. Okay, this one and we can have one from this register, another from the memory, and both can be in the memory. Okay, so this is called a general organization, general register organization. Fine. Now, another class of organization is called a stack organization. Here, we use a stack, and a stack has a push and pop operation that we have already discussed, and in this operation we store data from the top of the stack. And the stack of organization, operands are placed on a stack and operations are performed on the top of the stack, that is open end of the stack. So, operands are implicitly specified, that is more important to note down here, that is implied. Okay, here we can see that it is explicit, and here one is explicit and another is implied. Okay. So, this is very differentiating factor in the three classes, that how much explicit and implicit notion for the data that we are referring for operation is to be specified, and that is why it is classified in single general purpose and the stack organization. Okay. Now, we can do a push and pop operation in the stack organization. Now, if we have these three different, so we have various types, so we can perform various operations. Like for example, if we go for the accumulator, so all the operations are performed within the implied accumulator. So, that is a simple accumulator register that. Okay. So, consider this example, add x. So, what will happen at this stage? The accumulator content, okay, accumulator content is updated with the addition of accumulator and a data that is available at particular memory location x. So, this is a explicit notion and this is the implied notion, okay, and this is the explicit notion. Okay, so where X address is operand and the add instruction in this case results into operation this. Okay, the accumulator is accumulator register and MX memory operation symbolize the memory world located at address X. So from where this memory is being fetched, it is fetched through this outside connection and it is selected through multiplexer. Fine. Now there may be other possibilities like instructions format can be having 2 and 3 addresses also. Like here we have shown one example is this, another is this. Okay. So here you can see there are 3 explicit addresses R1, R2 and R3 is mentioned or other combination like memory. Okay. So the instruction format in this type of computer needs 3 address registers or address fields whatever. Thus the instruction for arithmetic addition may be written in the assembly language like this, and you know this assembly language instruction is a outcome that we have discussed previously in the starting of the topic, that first we write a C program, okay, then the compiler converts into a assembly language program, okay, then generates assembly program, that this assembly program that we are talking about. So we are, when we are writing this, okay, add R1, okay, R2 and R3. So this is the outcome of assembler. Okay. Finally, this add instruction goes to the assembler unit that generates the binary code. Okay. So we should understand this in your mind, that when we are performing this assembly language notion of instruction or understanding assembly notion of instruction, we are basically working on the registers or the modes or the reference or the formats of the capacity of the architecture or the organization of a system. So this particular 3 address notion has 3 explicit representation of addresses R1, R2 and R3. Okay. So it will perform an operation like this. The content of R1 will be the addition of register 2 and register 3, and it will be stored in R1. So number of address fields in this instruction can be reduced to form 3 to 2 destination register, and this is known as the 2 address instruction. So basically add R1, R2. So what will happen? The content of R1 is added with the R1 content with R2 and the result will be stored in R2. Okay. Similarly, we can have computers with multiple processors or registers used to move the instruction, okay, with the mnemonic move to symbolize the transfer instruction. Okay, so we want to move the content from register R2 to R1. So certainly we require 2 address instruction format, especially for the when we perform a move operation. There is no option. So 2 address instruction is required when we are performing a particular operation of move. Fine. Now, in the 0 address instruction that we have already told you about the organization of the computer, that is called the stack organization, and the 0 address is related to this particular organization. In the 0 address, we perform push and pop operation, and there is no explicit notion of addressing, there is a implied addressing. So basically we perform push and pop instruction which require an address field, thus instruction have push which does not require, okay. So we will push that data X to the top of the stack. Similarly, when we have pop, it will bring the data from the top. Now here we perform an operation. So it will perform operations with 2 items that are on the top of the stack. The instruction is not exactly referring any data. Okay, you can see no reference is given. So when we say add, what is happening? It is taking the top of the 2 stack elements and performing operation and storing the data back to the top of the stack. The stack computer contains an operation that code only with the no address field. Fine. Now, in terms of performance of the program, we should understand that each and every formats will have different lines of code in the assembly language program, and that will impact the performance of the computation in terms of time. So, let us have an example to solve a mathematical problem of x is equals to a plus b into c plus d. Okay. So, if we perform this using 3 address instruction in the assembly that is available, we can see with only 3 instructions, that is very important, 1, 2 and 3 assembly instruction, we can perform this particular task. So, we have used 3 address instruction and performed the first add R1 A comma B. So, the content of memory location A and memory location B is added and is stored in R1. Similarly, content of memory location C and D is read and added and is stored in R2. Now, we have 2 content R1 and R2 available in the register itself. Now, in the last instruction, we will read the content of R1 and R2 and use the operation multiply and is stored directly to the location memory X. This is 3 step. Now, if we do this same task with the 2 address, now you can see this is very important thing, that is important observation, and we should understand that 3 number of steps are required at the assembly level. Now, here you see how many steps are required for the same operation, 1, 2, then we have 3, then we have 4, then we have 5 and 6. Now, how many steps have increased? 3 more steps. So, we can simply say that the 3 address architecture or organization is fast, okay, than the 2 address instruction. Now, here we can see how it will proceed since it is a 2 address. So, first we will read the memory data at location A and store it at R1. So, we will use a move instruction, and finally, we will again choose a memory location B, okay, and add with the R1 directly instead of bringing increasing one instruction move R2 B, we will directly operate on B. So, the content of memory location B is added with R1 and the result is stored at R1. So, many times students usually think that why not we add one instruction R2 and read the data location B and stored. No, not required, because it is R1 is already available. So, we will read directly from the memory location B and add with the R1 and the store data at the R1. Fine. So, now by this time we have the data of A plus B available in the R1. Now, next we will again read the data in R2 from the memory location C, and we will add the result of D to R2. So, we have now the result available of C plus D in the result register R2. So, we have 2 data R1 and R2. Now, both data are in the register. So, we will apply simply multiplication operation, R1 multiplied by this R2 and the result will store, and finally, we will store back to the R1. Fine. Now, a very interesting thing that we can see in the 1 address, the number of instructions are increased further. Okay, you see 1 step, 2 step, 3 step, 4 step, 5 step, 6 step and 7 step. So, as you increase the number of addressing operands available like 3, 4, you will have less number of assembly language, and when you reduce that, you have more number of assembly language instruction. So, in 1 address, we have to perform first load, then we have to add B, then store back to the T result, then load C, then add, then multiply with T and then store. So, this will create a total 7 number of steps. Similarly, if you do for the 0 address, now you count this, how many steps are there? 1, 2, 3, 4, 5, 6, 7 and 8. So, out of this, which one is the slowest operation? Certainly, the 0 address instruction will be having the slowest operation. Fine. So, if we see all the instruction formats that you have learned till now, okay, as far as the organization, single accumulator, generalized organization, stock, they have different efficiency of execution of instruction, single accumulator will be slowest, then generalized is the fastest. Single accumulator is in between the slowest and the fastest, general is the fastest, and stack is the slowest. Okay, and we have also told you about the instruction set architecture, and that will be having different set of instructions for instruction set 1 and 2, and the instruction code is translated, machine higher level instruction is translated into machine code of the processor, and that is being executed, and that will be fetching the data from the register or the memory, and the three ways are single, general and stack organization. And we will see the execution of these instruction on the same objective. We will see that the time of operations of each on the each different organization will be different. So, here are number of steps required are 3, here are number 6, then we have 7, and finally at the 0 address we have 8 number. Okay. So, thank you my dear students for this understanding of instruction formats. We will meet in the next lecture for the addressing modes. Jai Hind.